class and we stopped there, right? So yeah, I think I need to start recording this also. The Laplacian operation is defined as uh, the divergence of the grad of a function. If the function we are considering is u, it could be vector or a scalar, and the grad of the function will give us uh, the grad value of the function, and after we get that, we apply the divergence operation on the output, right? So first we need to find the grad of the function, so we do that by in the last class. So the same operation we can see is used in divergence operation as well. The only difference is that in divergence operation we dot product the operation with the function. There's a dot product here, right? So this whole entire thing is the grad of u. This entire section is grad of u, and this entire section is the divergence operation. Divergence operation. So divergence operation is defined by this function as we discussed earlier, and the divergence operation is taken separately as like one of the vectors, and then we are taking the grad function, which is also defined by vectors and differentiation like operations, which is applied on a certain field, whether it's vector like scalar, right? So we can apply it on a field, right? And then we can get the dot product. In there, when we once we do the solving of this, we can actually take the dot product of I hat with I hat, right? And once we consider this first expression only, we can actually see that only the functions or the parts of the function which has the same vector um, will get added into the final sum. Other products between perpendicular components will result in zero, right? I hat and I hat across k hat will result in zero. K hat into I hat will be zero. So therefore, we only consider situations where we have I hat dot I hat, and then we only compute those expression values because j hat and I hat will zero. Likewise, other components which are perpendicular to each other will be zero when we take the dot product. So we can actually, by considering all that, we can actually get this final output where we hat and I hat, right? After taking the dot product between I hat and I hat, we are left with this expression. Then once we do the j hat and j hat, j hat dot j hat, we are left with this expression, right? So it said hat k hat and k hat. Once we do the dot product, we are left with this part. So we don't have any I hat, j hat, k hat components in the output, right? In this output, like in the U field, there could be some I hat, j hat, k hat values, which means this is a vector field. However, just the operation of this part will not have any vector components, and then we can actually find the value after we apply the vector field on this operation. After we apply this operation on the vector field, we can find the final output. It could be vector or a scalar. So this expression can be written like this. And then once we actually see some examples, we can see how it can be computed, right? So if we have expression like this, right, Laplacian function is defined by uh, the uh, second derivative with respect to x plus second derivative with respect to y plus second derivative with respect to z, right? So we need to apply those operations on the function, right? So once we take the second derivative uh, of this function, entire function with respect to x, only this part is remaining. So once we take the squared, dabba x squared of x squared plus the rest of it, y squared plus z squared plus dabba squared over dabba y squared. Then we are left with what? What is the answer for this? Can you answer this? So once we take the second derivative of this expression with respect to x, the only component that is valuable is this one, which is having the x, right? So once we take the second derivative of x squared, first we need to derive it once, and then it would be uh, 2x. And once we take the derivative again, we are left with 2, right? Can you get it? So same thing for the others as well. So once we do the second derivative of other components, in this first expression, the second derivative of other components with respect to x will be 0. This will be 0. And then in here with respect to y, this will be 0. This will be we can take the second derivative with respect to y first, right? Will be 2y. And then we take the second derivative again with respect to y, and that will be 2. So same thing will happen in here also. It will result in a 2. So in that case, we are left with 2, 2 and another 2. So we have the total output as 6. So I hope it is clear, right? So you can do for this expression as well, right? And then actually r in here I think is like x plus y plus z actually. Okay, I I believe, right? I need to like decide it, but anyway, let's take r as x plus y plus z, right? In that case, um, right? In that case, like what is the output? So you can derive that and you can see. So I think this is going to be actually a little bit difficult as well. So anyway, you just try these two once, right? Then we'll go to the curl operation. And the curl operation is basically defined using the usual operations that you have learned before. I hope you know about curl operation, right? So during, I think in your previous modules, you must have learned about this in your mathematics class. So basically, curl operation is defined using a determinant of one vector and another vector, right? So we are taking the determinant of one vector and another vector, where we define the I hat, j hat, and k hat as the top row. And then what we do is we follow a certain procedure to find the curl value. So we are actually solving this determinant, right? So we are once we are taking the determinant of two vectors like this, we first actually consider I hat, and then we take the multiplication between this cross multiplication between the components in this box. We take uh, we take the multiplication uh, with a z first, and then subtract with the multiplication that we get with ay, right? So this pattern goes for j as well, right? So however, the difference with j is that we actually do a difference in like sign in here in order to get the correct answer that uh, that follows this uh, determinant operation, right? So I can actually write it in here, right? So the determinant operation, right? Determinant operation of the I mean of this cross product between the grad operation and uh, the field that we are considering is taken by taking the dabba over dabba x, dabba over dabba y, dabba over dabba z components, right? Which is defined by this line. This operation is defined using dabba over dabba x I hat plus dabba over dabba y j hat plus dabba over dabba z k hat, right? So what we do is we take all these I hat, j hat, k hat components out, and we are remaining with these components, right? So these components we take out and we keep them under each of the I hat, j hat, and k hat vectors, right? So dabba over dabba x belong to I hat, dabba over dabba y belongs to j hat, dabba over dabba z belongs to k hat. And then once we know the whatever the values of this a vector has, let's say, has a certain function which says that ax I hat plus uh, sorry, ay j hat plus az k hat, right? So we can write this vector. This is a vector, right? This vector also we can write like this, right? Under each vector component that is corresponding, we can write like this. Do you have any difficulty understanding writing this determinant? If you have difficulties, let me know. Then we just follow this operation. So we first take the cross product between these vectors or components in this box, right? First we take dabba over dabba y az minus dabba over dabba z ay. First we take that and we multiply by I hat. That is one first component. Then we put a minus sign here. Okay, so I'm actually following a different different method than here. In here they have done changes of terms in here. However, I'm just writing in the like another method in here where we just do the same operation um, with the other set of vectors that is remaining once we take the j hat into consideration. So when we are considering j hat, we need to consider the cross product between these two. So we will be multiplying this dabba over dabba x, right? Dabba over dabba x az minus dabba over dabba z a x, right? Same. Now, when we consider this expression and this expression, they will be same, right? So I have just I'm having this first term in the in the first position, right? However, in here we have it in the second position, right? And the second term is in the first place in this expression, and then when we consider the signs are equal, but in here the sign is minus, in here the sign is plus. So therefore, once we take the minus sign of this expression, these terms get back to the order that this equation is having. So anyway, you can see that these both equations are equal. These are equal. So these both these equations are equal, right? So you just you can follow those two different methods to do the same thing. So once we take the k hat and do the operation, we have the k hat, right? So we have the k hat. So in that case, dabba over dabba x ay minus dabba over dabba x ay. Sorry. In first we take the multiplication here, and then we take the multiplication, right? Dabba over dabba y here. And then I will take the k hat here. So same operation, same expression that I have in here is coming here as well. So likewise, we can find the curl of the grad function and the a vector, right? So the curl operation is basically, giving us some important information about the vector field that we are considering, right? So this is a vector field, right? So if the vector field is given using this pattern, right? This is our vector field, let's say. In this region, some vectors are there, right? And then once we apply the curl on this vector operation, right? Vector operation, vector field, which is defined by A, right? This vector field will have some like components, I hat, j hat, and k hat. Once we apply this curl operation, it will show that there's some curl in this vector field, right? These vectors are circulating. Some circulation in the vectors is happening, right? So curl gives us like the circulation of a vector field, right? Curl gives us the circulation of a vector field. If there are some circulations in the vector field, the value of curl will be non-zero, right? So if there's some circulation, the value will be non-zero. If uh, if uh, if there's a circulation, right? So that is used for us to find circulations in our fields, right? If there are some circulations, then we can find using curl function, right? So curl function also you can solve some example sums, right? So these are some example sums. I think you can follow the same procedure to find the curl of a function, right? You can find the curl of these two expressions, right? So after that, we also have a certain conclusion that we can draw, right? So if there's a vector field that has zero divergence, then the field or the vector field is known to be solenoid. That means that if, for example, if we take a solenoid, right, the solenoid has a solenoid is basically formed by a metal wire which is wound around a certain metal core, right? So once we wind some metal wire around some kind of a core, then electromagnetic field is generated, around the like core, and the core is getting magnetized, and the north and south pole will be created, and the field that will be generated will be like this. The field lines will be going north to the south. Once we have these north and south poles together, once we consider certain surface, right? Once we consider certain surface, we can we can't see any lines that are going outward, right? We can't see any lines that are going outward and not coming back, right? If there's any field line that is going out, then that field line will come back as well, right? So if there's any line that is going out, for example, out of a certain closed surface that we are considering, that same like line will anyway come back into this volume, right? So the same strength that was going out will come back again. So the net effect will be zero. The net effect will be zero. There's no outgoing electric flux from the surface, from the closed surface, when there's a solenoid like this. So it might not be clear to you right now. It's okay. So what I'm saying is that there is no like electric field line that is going out and not coming back. If there's some electric field line, if it is a solenoid, right? So therefore, if it is a solenoid, the electric flux are known to be zero divergence. That means the divergence of the electric field lines is zero. That means that electric flux lines totally leaving that surface is zero. There's no such phenomena of electric field lines going totally outward and not returning back. In that case, that electric flux are known to be solenoidal. That means that electric field lines are staying within certain space all the time. Staying within this space all the time. They are not going outward and totally not like it is not like this, right? It is not like the electric flux lines are going out and that's all, right? In this case, like if we consider a certain closed surface, right? Let's say there's a closed surface and some electric flux lines are going out, but those electric field lines are not coming back. In that case, this is a diverging field, right? But if these lines are not returning back to our closed surface, then the electric field lines are diverging. But if those lines are coming back somehow, then we call that it is not diverging. It is not diverging. In that case, we call like solenoidal. That incident we call as solenoidal. And anyway, so if there's a vector field that does not have divergence, we call that that vector field is solenoidal. That means this electric field lines are coming back to where it was originated. And if there's a vector field with zero curl, that means that vector field does not have any curl operations happening in that field. Right? Earlier we saw that there's some vector fields that have curls in that, right? So that vector field, the vectors are moving in a curl, like they have circular rotations. In that case, the electric field is known to be uh, curly, or there's some curl in the field. If there's no curl, then our field could be moving in this kind of direction without any kind of diverge or some kind of a diversion in the direction. In that case, there's no curl in here, right? If all the electric fields are in a certain direction, there's no curl in this, so it is irrotational. And then we can call zero gradient scalar field we can actually consider to be um, like constant gradient field, right? So that means that our uh, vector field does not have any maximum and minimum point. right? Our vector field does not have any maximum minimum points. In that case, that vector field will be like constant value. There's no minimum maximum point. There's only constant value for the vector field at every point. If we take the height of that vector field or something, it will be constant all the time. So there's no minimum. There's no point where there's a slope, right? So likewise, we can consider that the constant and behaviors are shown by this vector. I mean, the behavior of a vector field are shown by the these operations, right? We can check those operations and we can find the behavior of a vector and a vector field, right? So basically, those are the things that define the vector operations, right? So I will like try to also a little bit, not too much. I think I have I think spent a lot of time for setting up the connection today. Sorry about that. So the coordinate system, as we discussed in the last class, it was like introduced by the scientist called Rene Descartes, and he was the first person to denote something in a graphical manner in a certain graphical space. Like was to in general like understand like in with reference to the some kind of origin, what is the position of a certain like point or some kind of object or some kind of a current or something moving or staying in one place. So with reference to origin, we can find that position of a certain object. So this is very important for us, and therefore we have different types of coordinate systems that we will be considering. We have Cartesian coordinate systems, which will be run using x, y, z. Right. So I will go to that diagram. So basically, this is the Cartesian coordinate plane. We have x, y, and z. Right. And one thing to note is that in this course and in physics, basically, we have the x, y, z coordinate axis represented using um, x being in the first axis, and then y, and then z. Like in this direction only, we have x, y, z, right? So what I'm saying is that we don't say x is in this direction, y is in this direction, z is in this is wrong. This is not the correct notation in physics and in electromagnetism, right? We always have to use x is in this direction, y is in this direction, and z is in this direction only, right? So we will be following this standard all throughout our lesson. So we will be always representing this axis as x, y axis as this, and the z axis perpendicular to both x, y. So that is a convention, right? So and then we will be talking about our the Cartesian coordinates, cylindrical coordinate system, right? So cylindrical coordinate systems are also uh, like important coordinate systems, and they are defined differently uh, than the Cartesian coordinate systems, right? So the cylindrical coordinate system is based like basic parameters like the radius to the point that we consider, and the angle phi to the point that we consider, and the z height, right? So we first take the magnitude from the origin to the point that we consider, and that we call as the radius, right? And the angle that we measure from the x-axis to the point to the position that we consider, we call as phi, right? So uh, it is also, necessary for us to understand that the standard phi angle is always measured from the x-axis, right? Not from y-axis. Always we need to measure from the x-axis, not from the y-axis or z-axis, right? That is one special thing about the coordinate systems, right? So cylindrical coordinate system, spherical coordinate system also, they have those standards. So we need to like use those standards all the time, right? And then once we have the phi angle, the other important thing is the z-axis, right? Z-axis is same as the XYZ plane, right? Same as the XYZ Cartesian coordinate system, right? There's no difference between Z value in the cylindrical coordinate system and the Cartesian coordinate system, right? Z will be same for both cylindrical and Cartesian. So the only difference that we see between cylindrical and Cartesian is the definition of the point that we are considering with respect to the radius and the angle, right? So earlier in the Cartesian plane, we used the XY coordinates, but now we are using the R value and the phi value, right? So that is the basic difference, right? So we can see that in the cylindrical coordinate. So I'm just saying this as a like overview. We will go through these in detail in the next class as well, right? And then we have the spherical coordinate system, right? So in there, some another parameter is getting added, right? In that case, if we have some position that we want to define using our coordinate system, right? Our spherical coordinate system, then we need to consider both, we have to consider three parameters: the length or radius from the origin to the point that we consider, and then the angle that we can consider from the x-axis to that point, which is defined by phi, and then the angle that we can define from the z-axis towards this point, right? So this angle is totally like a spatial angle, right? Like it comes from the z-axis to the point that we consider, which is in any like in a midpoint in the space, right? So this this theta value will always start being measured from the z-axis, always. So this is the standard for the cylinder, so spherical axis, spherical coordinates, right? So those are the basic things I wanted to share with you. So regarding the coordinate systems for now, right? In the next class, I will actually in detail go through these expressions. Actually, these expressions are also like kind of having a lot of like complex kind of looking mathematical expressions, but um, they are actually easy to understand if you can understand the concept. And also this is not something I will be asking in the for example in the exam, because like I don't want to just know whether you know the coordinate system, but I want you to apply it on a certain system and solve a certain problem, right? So that is what I will be expecting you. So therefore don't be scared about the mathematical look of this coordinate system. That is one thing. Second thing is that I have also uploaded a document in LMS which has so many details about these coordinate systems, right? If you want to learn about the coordinate systems, I think that is the best document that you can use. I don't know whether you can see my screen, right? I want you to actually uh, see it actually. I hope you can see. Okay. So if you have any questions regarding the course and anything else, you can let me know. So I think, okay, sorry. Have gone to a different, sorry. Have oh, in this one, you can go to the resource section. There's some PDF that is there regarding coordinate systems. Right? This is the one, right? So in this one, you can read this documentation, right? So you can actually go through whatever the important facts in this document, right? It is having most of all the important facts regarding the coordinate system, right? So You can go through this document. I have only taken out the important factors that are required for me to like conduct the electromagnetism part. Anything else that you want to know, you can read this document and you can get more information. It's so important to have the idea about the coordinate systems, which is useful in not only in electromagnetism but in other sums and other situations as well. So that's all actually I wanted to mention to you. So thank you for attending today's class. If you have any questions, I can answer. And with that, I'm hoping to end today's class. Right. So I hope you learned something. Right. So if you have any questions, you can let me know. Right. I'm happy to answer those questions. Apart from that, like in the next class, I will be doing the coordinate system. And then afterwards, I will be starting with the electric charges and Coulomb's law. So I will be starting about starting content about the electric fields, and I will be starting the kind of the theory part of actual electromagnetism, and I will be proceeding with that. So currently, I'm at the position where I'm like teaching Gaussian law to the regular student. So I will be, I think, be able to catch up with the regular students easily in this online class as well. So we will get like go ahead like that, right? So that's all for today. So thank you for attending today's class. I will end the meeting. Okay, so thank you so much. Bye.